Hello everyone. In this video we are going to see several basic yet very important operations on images that you can do in MATLAB. So let's start with the very simple one, basically arithmetic operations on the images and first adding and subtracting. So you can add images together. There is a command IMAdd, or you can simply add corresponding pixels of two images together. You need the two images F and G to be the same size. Here row R and C are row and column index, and alpha 1 and alpha 2 are two weights that you use to add the two images together. If you do it, that's what we call alpha blending. So alpha blending is basically a linear combination of two images. Typically, they choose one of the gains to be 1 minus the other gain. So basically, sum of the two gains is equal to 1, but not necessarily. The other thing you have to pay attention to is when the two pixels are having high values and you're adding them together, right? If you don't choose the gains alpha 1 and alpha 2 the same way I told you, one alpha, the other one 1 minus alpha, and alpha is less than 1, then you will have saturation at those pixels. So if you're adding a white region, let's say here, and then, or roughly white region, let's say here, right here above Bill Gates' head, and something here, and again, these alphas are not necessarily less than 1, then you're adding white over white and you have a lot of saturation. Or there might be some other areas that they are not perfectly white, they are shades of gray, but when you add them together, here you're going to see white. So if you don't observe the same way that I told you, alpha 1 and alpha 2, both less than 1, and choose alpha 2 to be 1 minus alpha 1, then you might have a lot of white areas over basically or areas over saturation where you don't see any of the details. Okay, so here you can do this alpha blending using what we call these images on the right. We call them the ground truth, or you can just do it simply. So here in my code, I'm using a little bit of the ground truth, but I have changed the ground truth from what you see here for the entire body of Gates to only the head of him, and I'm not using the ground truth of the skyscrapers at all. So I'm not going to get something exactly like this with his hands also all over the skyscrapers. I'm going to only show his head basically over the rest of the thing. So here, if I run this section for you, right? So first I clean up everything and then I run this section. You'll see, and here I'm also using some image pixel-wise multiplication that I'm going to explain to you. So definitely I'm not going to do exactly what you see in that image, but you see, right, that I read the skyscrapers image, I read the Gates image, and I only used the head part of him. And how did I do it? As we'll see here, actually I'm using both gains of 1. You might say, well, that's exactly in contrast to what you said right here. That's right. But here I'm not simply adding the entire two images together. What I'm doing is I'm only considering one portion of this image, which is only the head. I only keep that part and do not use the rest of it. And in the other image, the skyscraper, I'm not using any part of the skyscraper that has overlap with the head of Bill Gates. Okay, so I'm basically using this ground truth of the head, which if I show you right here, I call it image 2 ground truth. Okay, so it is this guy. Let me show you. Okay, it's only this head. In the head area, I show the Gates picture. In the complement of that, which is the black area, I'm showing the skyscraper. So there is no area that the two images can have overlap and their white pixels or big light intensity pixels can be added and give me a lot of white areas. What I told you is for the case that you see here, I'm using Pixelwise product, and we're going to discuss this in more details, but here I'm using the ground truth, multiplying it pixel-wise by the image, and then I'm just using gains of 1. The case that I told you is if this image final was simply a linear combination of the two, so it was like, let's say, some alpha 1 times image 1, as simple as that, and then plus some alpha 2 times image 2. And here, if I don't use the rule, even if I use something as simple as, let's say, 0.8 and maybe 0.7, both less than 1, but clearly the summation is not less than 1. And I use this for the alpha blending, correct? Then let's see what happens here. So let me not forget to add the asterisk. So I run it one more time here, clean up, redo this part, and you see here, clearly in this region, and in this region, I have a ton of what? Super bright areas that are hiding the details behind them because some of the pixels clearly is more than 1 or more than 255 for uint 8 or 1 for normalized double images, which clearly saturate the area. So if I want to do that, I better use 0.8 and 0.2, okay? So if I run it one more time, you see at least I do not have any super white region anywhere, right? And it's a mix of the two images. Which image is dominant? The skyscraper. Why? Because the weight of it is bigger than the weight of the other one. If I want an equal weight for them, then I use 0.5 and 0.5. So now if you look at it, you see it's kind of in between the two. So which one you want to focus more, you can use a bigger weight. But again, you're gonna have some areas that are kind of meaningless because here you have the sky and the curtain. Here you have the hands and the skyscrapers, so you never get any image as clean as this one unless you use this black and white images, which we call masks or ground truth, basically, which we'll talk about it later. But just wanted to tell you the simple image addition, but as I said, you can do subtraction of images. Again, the two images have to be the same size. And you might say, okay, well, this alpha blending can kind of give me some of those artistic effects, right? Let's say if I have never been to the Eiffel Tower and I want to show my friends, hey, look, I have been to the Eiffel Tower. What would you do? You take a picture of the Eiffel Tower, you take a picture of yourself, and then overlay your picture on the Eiffel Tower. And guess what? Instead of spending so many $1,000s going to Paris, if it's just for a show off, then you can just simply do it in MATLAB or Photoshop or something, right? Basically do some processing on your picture. But what about the image subtraction? Why should you subtract the images? Well, one of the major things that you can see is called the background subtraction. If you have a stationary background and you want to detect what comes in front of the camera, right? If you want to detect the moving objects in front of the camera, then all you need to do is to subtract that stationary background image from your current frame, from what you see at the moment. If you subtract the two, then all you will see, and you apply a threshold to it, which is our next topic, thresholding or binarizing the image, then you can basically find the areas in the image that we call foreground. And foreground are the areas in an image that move. Their pixel values do change. Backgrounds are the pixels that their values do not change. Okay, so a simple subtraction can tell you if you have any object in front of the camera or you don't. For example, the traffic lights, you see they all have cameras. And a simple algorithm you can apply in them to see whether there is any car behind the red light waiting. So they send a signal and turn the light of the red to green and the green to red. So they give the right of the way to another street, is by simple background subtraction, okay, and thresholding. Now, it comes with some problems. It's not typically as simple as just subtracting. Let me show you that. So if I do the same two images that you can see here, this is background, this is the current frame. The only object added to the scene is the boat. So simply if I subtract them, I should be able to see a boat, right? Is that going to be the case? Well, let's find out. So here, also, let me do something here. There we go. So here, if I come and I read them and I subtract, and then I use some threshold. Now here, I converted the images into double format instead of uint8. Why? Because uint8 only goes from 0 to 255. And when you subtract two objects from each other, then if your object is what? Is darker than the background, what's going to happen? Remember, you're subtracting current frame from the background. So if a pixel here on this boat is darker than the water, what's going to happen? Right? Let's say here at this pixel, you're going to have, let's say the light intensity is like 20, but at water is like 100. So the subtraction will be like -80. But uint8 images are only between 0 to 255. They cannot go negative. So what's going to happen? Yes, although there is something, although the difference is not 0, but because the difference is negative, what's going to happen is, because it's uint8, the difference is still a uint8 image, it's going to truncate it to 0. It's going to remove it and eliminate it and make it 0. So that portion of the boat where it's darker than the background, you're not going to detect. This portion of it, basically, you only see the portion of the foreground that is brighter than the background, not the other way around. Okay, if you simply subtract, unless not only you subtract foreground minus background, you also add background minus foreground and add them together. So all pixels of the foreground that are brighter or darker than the background, you can select. So if you want not to convert your images into double and still only allowing positive numbers, then you have to say f minus g plus g minus f. That way you can detect all pixels of the foreground, whether darker or brighter. But the good thing is when you convert it to double, now double can take over negative numbers. So now I can simply take over negative numbers, and that's what I did. I converted my images. First of all, I resized both of my images to the same size. They were not exactly the same. So I make sure they are the same size. We talk about resizing in a minute. I converted them to grayscale and then I doubled them. Then I divided both images by their maximum. So that's what we call normalization of the images. Let me add something for you here. Image normalization. Make sure the maximum in both images is 1, because one of the images in general could be a little bit more brighter than the other. Why? Because there was more light when you took pictures, right? So here you are kind of eliminating the effect of more light or less light when you took the picture. Then here you see I'm taking the difference. And then here I'm applying a threshold, which we're going to talk about in a second. But if I run this, let me show you. So here is what you get. This is the background. This is both foreground and background. The object is added. This is the difference between them. You see, I could detect all of the pixels that are different. I could detect the entire boat. But that's not the only thing. The rest of the image is not all 0. It should be all black. Because if they're all the same, they should all be perfectly black. But it's not. Why it's not? Guess what? If you look at these two images, there are some other differences between them. One of them are these areas that you can see in the binarized version of the image. Not only you see the boat, you see what? You see some white areas here, which are the reflections. So not only you can capture the boat if there is some reflection on some parts of water in the foreground, but not in the background, you're going to detect them as well. You're going to see and detect them. And there is a little bit, again, more reflection on whatever this one is. I don't know, it's another boat or some seat or something. Seems like another boat. So this area is a little bit brighter, so there are some also artifacts in this area. So when you look at this binary image, where I use the threshold of 0.15, not every white pixel means necessarily they are moving. Means they are a part of the foreground and not part of the background. They are basically artifacts. So image difference not only show you moving objects, it also shows you the areas where the light intensity dramatically changed, like reflection areas or any other thing. And so you would never in reality get something as perfect as this one, unless you do some further operations on this kind of binary image, which we'll talk about in a future videos, called morphological operations. Okay, so I'll show you, if you have something like this, is there any way that I can convert it to something clean and nice like this? Most of the times, yes. Again, that topic, as I told you, is called morphological operations, which are the operations you do on binary images, or on zeros and ones. That's a separate video of its own. We'll talk about it later. So now here I mentioned several times that I applied what? I applied some threshold on this image difference, and here you see the threshold of 0.15 to convert it to black and white, because this is still grayscale. How did I go from this image on the top to the one on the bottom? That is the next topic, which is called image thresholding or binarization. And it's very simple. It's basically a saturation thing. So you say, for example, if in this image difference here, this F for you is like the image difference. Say if in this image difference, let's say, if the value of the light intensity at that location, at any location R and C, if it's bigger than some threshold, set it to 1. If it's less than that threshold or equal, set it to what? 0. As simple as that. Pixels brighter than some value are going to be 1. Pixel darker than some value will be 0 or black. And here you can see that to this cameraman image. This is an image called the cameraman, very famous in image processing. And you see the pixels less than some threshold are black, anything above that are white. So that's the result that you see. Clearly the result big time depends on what? This threshold. If this threshold changes, then definitely your appearance of the image does change. So here I'll show you in the next part. I read the cameraman and then I use 3 different thresholds, 50, 100, and 150. Remember, the max value of the pixels are 255. So I'm using 3 separate levels, 3 separate thresholds. And here, if I run the code for you, you can see the result. As you can see, the bigger the threshold, the larger or the more expanded the black area is going to be. Because I do not count something as white unless their values is more than 150. And clearly, there are not as many pixels above 150 as they are above 50. So definitely here I'm counting a lot more as black because their values are below 150 compared to here where I only count them black if their values is less than 50. Right? So clearly if you want more white areas, you have to bring down the threshold. If you want more black areas, you have to raise the threshold. Okay, so this is simply what we call image thresholding or image binarization. And what's good about binarization? The binarization comes when you have to decide on something, when you have to do some classifications, when you have to divide the image into, let's say, foreground and background, object 1 and object 2. So you say, for example, all the white areas are object 1, all the black areas are object 2 or something. When you want to do a binary classification, object 1, object 2, then this thresholding or binarization or foreground and background, this is where this guy is extremely useful. The other thing I mentioned in the first image for you was image pixel-wise multiplication, which the good thing that gives you is if you give it a binary image like this one in the middle, which as I told you we call it a mask, then if you do a pixel-wise multiplication of your image with this mask, which you can see here in the middle, then this one, which we call the mask, then if you do a dot product of your image with the mask, what would you get? So any area in your image that is pixel multiplied pixel-wise by the white area is going to be saved or kept. Any region of the image that is multiplied by a 0 in the black area is going to be suppressed, right? So that's what gives you a region of interest or ROI. Just multiply the image by the mask and anything inside the mask will be kept for you. Gives you, say, hey, the only thing in this image I want to focus on all the time is this entrance door, right? So if I just create a mask around that entrance door, and that allows me to have this image instead of this guy. And what's good about this image on the right? Well, it has a lot less light intensity values to be processed, correct? It has a bunch of zeros that they never change, so any pixel in these areas you can literally discard. You don't care about them. You only care about the pixels in this area for which the value is bigger than 0, and you're going to process them. Okay, so masking images and extracting regions of interest is a simple thing that you can do with what? Image pixel-wise multiplication, and that's exactly what I did in the first demo that I showed you. If you go back here, you see that I extracted the ground truth of the Bill Gates, which was his head really, and the Bill Gates, and then what? Here, if you can take a look, let me do this one again. What I did is I'm multiplying the image 1, which is what? The skyscraper, by what? By anywhere that is not of image ground truth 2. Image ground truth 2 is the head of Gates. I'm saying anywhere that is not of that. Basically anywhere that is white, which is his head, neglected anywhere else that is not his head, use that and multiply it by image 1. And anywhere that is his head multiplied by image 2. So basically from image 2, which is this picture, only use the area that is the head. From image 1, only use the areas that is not the head. And you see here again, I'm using what? Pixel-wise product. I add them together, and that allows me to get what? To get let me clean up. And let me run this for you one more time. It allows you clearly to see the results here. So here we go. Right, you see? And again, for it, I used this image number 2 ground truth, which is this one. And for it, I also used the not of this, which is this one, right? So this one is pixel-wise multiplied by the skyscraper. This one is pixel-wise multiplied by the cold picture of Gates. And the summation of the two is this that you can see. So this is pixel-wise multiplication, regions of interest. Another thing that you see I used in several of these lines of code is the command resize, which is basically to change the size of an image, correct? If you want to change the size of an image, make it larger or smaller, you can use image resizing. Now the question is, why should you resize the image to smaller size or to a larger size? First of all, what's the application? Second of all, how would you do it? So first of all, why should you make an image smaller? Clearly, making the image smaller is meaningful when you want to do processing on the images, when you want to do computer vision analysis or anything, and you need to do a ton of calculations. So, of course, having a smaller image means a lot more, a lot less, a lot fewer pixels to deal with. So downsampling or resizing the image to smaller size, definitely good for computation and memory basically usage, bringing those down. What about upsampling? Where would you resize the image to a bigger size? That's where if you want to zoom into an image, right? And that's what you do in many of the cases. Look here, when I go to view in Microsoft OneNote and I use zoom out, right, or zoom in, zoom out, I'm making it smaller, and zoom in, I'm making it what? Bigger. So that's exactly the resizing. So if you want to see some detail with the bigger size, then you can basically make the image bigger. Now, when the original image has not a lot of pixels in it, it's not high quality HD pictures, when you resize them to a larger size, you're going to see artifacts, okay? You're never going to see a very beautiful picture. You're going to see pixelations, as you can see here in this image Barbara. You see, this is the size of the image or something close, but now when I made it like 4 times bigger, 16 in general, 4 times in each direction, you see clearly around the nose, face, and any edge, you see a lot of pixelations. So remember, there is a command in MATLAB, and if you want, you can program it yourself to resize an image, but you cannot do magic. You cannot make a small image that is low quality to a bigger image that is high quality or the same quality. It's not going to happen. Anytime you upsample, you're definitely going to lose quality. So now the question is, how would you do that? Well, downsampling is actually not as hard. Let's say here I have a 4x4 block, and I want to replace this 4x4 block into a 2x2 block. So I want to resize the image in each direction by a factor of 2. How do I do that? One of the methods that is very common is called pooling. Okay, pooling is what? Basically, if it's a factor of 2, you are going to choose each 2x2 block and convert it into a 1x1 block. How would you go from 4 numbers to what? To one single number? There are several ways you can do it. One of them is to take, let's say, the 1 pixel out of the 4. Like what? Maybe the top left corner. So from each block, you only pick the top left corner of that block, which is here what? 2. Then you go to the next block, again go to the top left corner, that's 7. You go to this block, top left corner, that's 8, and then this one is what? 2. So you can pick a specific location out of the block. Another better way is, instead of that, you took the average. So take the average of these 4 numbers, right? That's 8 and 9, that's 17 divided by 4 is 4.25. And if your image is not double, if this image was u int 8, and you don't force them to be double and then do the averaging, what's going to happen? If it's double, it can hold to these decimals. If it's not double, then it forced this 4.25 to be 4. This one to be 4, this one to be 4, and this one actually 3.5. It's going to be 4 too if you want to round it. Okay, so definitely this is another. Or you can use a max operation, or you can use a min operation, or a median. That's another thing that many people do, and we'll talk about it later separately in filtering images. Instead of averaging, they can use the median of the block. And this median is very good later, as we'll see, when you want to denoise the image. If the image has noise, then using median values is removing a lot of noise out of the image. But clearly picking one pixel out of so many, or average or min or max of them, even in this downsampled image, you are going to get an image that does not have as good as a quality as the original one. So downsampling can definitely also, just like upsampling, can come with loss of image quality, okay? But that's a very simple strategy to do. For upsampling, it needs a little bit more computation. How would you do that? Well, there are so many things you can do. Let's say, for example, here you want to go from this 3x3 block to this 5x5 block. How would you do that? There are several ways. There is what we call nearest neighbor interpolation, there is bilinear interpolation, there is bicubing interpolation, etc. So, like what? For example, if I want to do nearest neighbor, what do you do? So here, in this picture on the right, you see I have the original 3x3 image where each green location is the center of one of those 3x3 blocks or cells. On the top of this 3x3, I overlaid the 5x5. So now the reds are the pixel values for each cell in a 5x5. But here you see I made the 5x5 and 3x3 to be the same size. Good. So now if I know the green values, because I know my original, this is your original image, remember, and this is your upsampled image, which you have to find. So you know the green values, your goal is to find the red values. How do you do it? If I use the nearest neighbor, as simple as it gets, I go, let's say, to this pixel here. And I say, well, how much is it? Well, I look from all of the green values. Oh, excuse me. I look from all of the green values. I see which one is the closest to this red one. And it's clearly what? This guy here. So I say this red has to be the same as this green, right? Then if I go what? So this one is going to be the same as this. Then I go to this. Which one of the greens is closer? So I have two neighbors, this one and this one, but this one on the left is closer. So guess what? I'm going to choose the one on the left. So this one is going to be the same as this. Then I go to this one. Clearly, the green next to it is the one right below it. I go to this one. This is closer to this. This is closer to that, and so on and so forth. This is closer to this. Right here, this is closer to that, and just keep going. This is to this, right? This one is to this one to this one, and just keep going. If it perfectly aligns, then of course it's perfectly the closest, right? And so on and so forth. So I can use a nearest neighbor and assign the values of the unknown red pixels. Another way that is a little bit better than this nearest neighbor is to do interpolation. How would you do the interpolation? You either use linear functions or use cubic functions. So then why do we call it bilinear? I'll show you. So what is bilinear here? Let me show you that one. So, and why should I do that? Why shouldn't I not stick to that nearest neighbor, right? Because that's a simple method. This nearest neighbor is very efficient and fast. What's the problem with it? The problem is the result of it are quite pixelated. So here you can see if I go from this 3 to that 5 as I told you, and if you look at clearly this image Barbara, you see here I upsampled by a factor of 4 in each direction. Definitely you see a lot of pixelations, right? Just look at these areas and you definitely see around these edges with high frequencies, you have a lot of pixelations. Okay, so is there anybody that can make this result a little bit at least smoother, if not better quality, which you cannot get, at least smoother, not a lot of pixelations? The answer is yes, you do interpolations, bilinear or cubic. Cubic is better than bilinear, but I want to just show you how bilinear works. So in bilinear, you use basically the 4 nearest what? Green points for each red point and use a weighted sum of them. So last time we only chose one of what? The neighbors, the nearest one, and we pick the value of that. This time we choose 4 of the green ones that are closest to the red one, and then instead of choosing any of them, we use a weighted average of those. So for example, let's look at this picture here. So here you have these 4 pixels in green, 192, 21, 231, and 60. And if I tell you, let's say, what is the value of this red in the middle, right, which is between these 4, how would you find it? Well, the way to go about it is this. First of all, I can find these other red ones that I have around it, like what? Like this one here. If I can get that one and this one, they can help a lot to get ultimately to this middle one. So how can I get this red one here, which is between this 192 and 21? Between 192 and 21, this red one here, I use a linear interpolation. So if this is 192, this is 21, how much is this? It depends on the distance between them. So basically, the closer this red pixel is to any of the green ones, the bigger weight that green one carries. So here you see clearly this distance is smaller than this one. This D1 is definitely less than D2. So the weight of value to anyone is going to be bigger than the weight of 192 because it's closer to it. So what I can do is this. If the location of this pixel green is 1 in the horizontal direction or column index, and the green is pixel 2, this red falls at location 1.6. Okay, and now based on 1.6, 1, and 2, it's a simple linear interpolation to find what? 89. So I can say basically like 89 minus 21 divided by 192 minus 21 should be the same as 1.6 minus 2 divided by 1 minus 2, right? If this is your unknown x, a simple proportion would give you the value of 89. Okay, now knowing that this one is 89 and this one is 113, is that enough to calculate this middle point? The answer is no, because each point can always come from the 2 neighbors of it, right? Above and below it, or left and right of it. Here, for this red one, I could only find 2 values, 89 and 113 on one side of it. So I need to find this location at least so I can do a horizontal interpolation, or I should do this one where I do a vertical interpolation between that one and 89 and get this middle point. So first thing, I need an extra point like this 147. For that, now remember that this 147 is not an actual new pixel location. It's just one that you need to calculate, an imaginary one, in order to be able to calculate the middle one. So this 147, although not any of the new locations, you see it's like here instead of this one. It's this one. Can I find it? Yes. I do a linear relation between 21 and 231, as you can see here. And when I did that, the answer was 147. Correct? I can do that one. Or I can find this guy here and do another interpolation, this time in this vertical direction. But it's enough to do it in one direction, and either direction you do it, the result is the same. So now that basically, let me tell you, now that I know this point. I know this point, and I found one imaginary point, this point. That's enough. Actually, I did not need this vertical one, so I did not really need to calculate this. Once I found this guy here, which as you see I did, and the value of it was 113, and I found this one, which was 147, then between 113 and 147, I can find the pixel of interest, which here you can see is 133. So the middle one should be what? 133, and that's enough. Could I do it another way? Sure. Another way was, instead of that, I found this guy, which you can see it was 89. I could find the imaginary point here between these two. If I found that, right, let's see if I have it anywhere, 163. If I do an interpolation between 163 and 89, again, this guy will turn out to be 133. So it doesn't matter how you do it, linear interpolation horizontally or vertically. You can do it either way. The result, as you can see in any of these methods, is what? The same as 133. It does not make any difference. That's why you call it bilinear, which means whether I do it linear horizontally or linear vertically, it's the same. Now, bilinear interpolation, if you look, compared to the nearest neighbor, can definitely give you a lot better result. Look at the one on the right and compare it to the one on the left. Look at all these pixelations here. You do not see any of that on the right side, right? Absolutely smoother, although it's a little bit blurred, but at least if I wanted to personally prefer one, I prefer the one on the right. Okay, now there is one bicubic where you have to have more than 2 pixels around. You have to find a cubic relation, so you need 4 pixels around it, around any point. So this time you need all 4 of these. And actually you need 2 more in each direction because it's bicubic, so you do a cubic horizontal or cubic vertical. So basically you need 8 neighbors, or at least 4 in each direction, and you can do a cubic interpolation instead of a linear interpolation. The result of that is even better than bilinear. And in MATLAB, the command to go about it is resize. If you look here, I passed the image to resize. I passed to it the new dimension, and here I passed to it what? The method, whether it's bicubic, whether it's what? Bilinear, whether it's nearest neighborhood or anything. The default in MATLAB is bicubic. Okay, if I am not mistaken. Let me check that. I don't want to say something that is not true. So the command resize and method, you see I have nearest, bilinear, bicubic, and which one is the default? Method bicubic. That's right. You see bicubic is the default. There we go. So it was right. And nearest, bilinear, or bicubic are the methods in MATLAB. So you can do it using resize. You don't need to write a code for it. It's already written. That's the advantage of image processing toolbox in MATLAB. You can perform all of these calculations using a simple command and not start from scratch for your own application. Are there other stuff in MATLAB that you need to know about manipulating images? Absolutely. You can rotate images for a specific angle. You can translate the images for so many pixels along X, so many pixels along Y. You can do a cropping. You can flip the images, and you can apply advanced transformations on the images like affine or projective. So let me show you a few of, or all of them actually. So what are these here? So the command rotate, which rotates the image for you. Go down here. I read the image Barbara, and I use the command rotate. All you need to pass to it is the angle. The angle is measured counterclockwise positive, and it is in degrees. And since the images are moved, all the pixels are moved, you have to do some interpolation if you want to keep the result smooth. So here I used still bicubic interpolation to make the result smooth. And the other thing is, when you rotate an image, the result is going to be bigger than the original one. And all of the areas that are new and they are not a part of the original image, it can fill them with black or white or anything. So here, look, if I just run this section for you, here we go. This is the original image, Barbara, and this is the original image rotated with 30 degrees counterclockwise. As you can see, these areas are all filled with black. Okay, and the image rotated is definitely bigger than original. Look at the size. The original image 6, if you look at it, is 512 by 512, while image rotated 6, if you look at it here, you can see 700 by 700. Okay, so clearly it is bigger than that. What else can you do? You can crop the image. So here there is a cropped version of the image, and here there is a translated version of the image. So I shifted all pixels 50 units horizontally and 100 pixels vertically, as you can see, right? So it grabs that corner and bring everything down, and the rest of the image that is left blank, you can fill it with black or any other value that you want. So this one is using the command imtranslate, which shifts or translate the image. This is using the command imcrop. What do you pass to the imcrop? You pass to it the top left corner of the location of the crop and the size of the rectangle for the crop. How many pixels horizontally, how many pixels vertically to choose for the window of the crop, right? So here, if you look at my code, I said go to the location 2, 50, and 25, x25 or column 25, row 250, row 25, and then for 180 pixels horizontal and 202 pixels vertical, draw a window, and then whatever inside the window, grab it, the rest of it throw away. So clearly the cropped image is way smaller than original image, the way I gave it. Right? And then for imtranslate, I say translate the image 50 units in the horizontal direction, 100 units in the vertical direction, and fill the rest of it that is left with black. Okay, fill values with black. If I wanted, I could say fill it with gray or fill it with what? With white. Okay, clearly you see the image cropped is less than the original image, but the image translate is definitely what? The same size as the original image. So rotation and cropping do change the size, translation doesn't. Okay, please keep that in mind. And here I wanted to show you, you see here I filled it with white. I used 255 here. Okay, now, so I showed you these four. What else can you do to the image? One of the things you can do to the image is to flip the image. So remember, if I show you the original one, let me show you the original one. This is the original image, Barbara. You see she's clearly facing left, right? But here I can do a flip version of the image. Look at that. This image here on the top left, this one is flipped horizontally. So the right side becomes left and the left side becomes right, and then I can flip that image vertically, which the top goes to the bottom goes to the top. So I can do a flip, and those are simply using the command flip left, right, and flip up, down. Flip LR and flip what? UD. So I can do the flipping of the image if I want to. And the most advanced kind of things I can do to the image are basically transformations with some given matrix. So here, in general, I can pass to it a 3x3 matrix to do the transformation. So basically, it multiplies each pixel in the image by this 3 by 3 and gives you the new location for that light intensity. Now you might say, well, the pixels are two values only, horizontal and vertical, u and v. How come you can use a 3 by 3? Well, use the homogeneous coordinate. So if the pixel is u and v, you add a 1 to it, you multiply it, and it gives you u prime, v prime, and 1. And whatever light intensity that in the original image you had in location u and v, now you show it in location what? U prime and v prime. Clearly, the last one is going to be a redundant equation, which is the last row times this last column. So you cannot just plug in any number that you want in this matrix. In general, you can show if your matrix is 3 by 3, you cannot simply use 9 arbitrary numbers. This number definitely ought to be a 1, and all you can have is really 8 numbers that you can individually pick. So we say this general format of the transformation has what we call 8 degrees of freedom, or 8 parameters to choose. Now, if you choose all of these 8 individually the way you like, we call it a projective transformation. If not all of these 8s are independent, only 6 of them are independent, then we call it an affine transformation, 6. There is other one, if there are 4 of them that are independent, then we call it the similarity transform, and so on and so forth. So what's the difference between them in the appearance and mathematically? So the projective, which is the most general case, you select all 8 numbers, A1, B1, A2, B2, A3, A4, C1, C2, all arbitrary. What does it do physically to the image? Basically, it takes, if you want, you can take a square with 4 known corners, red, green, black, and blue, and transform it into what we call a quadrilateral. Okay, so you convert a square to a what? To a quad, let me write it down, quadrilateral. An object with 4 sides. Does this transformation in general preserve the size? No. The length of the members? No. The angle between the members? No. Parallelism? No. For example, the line going from black to red and blue to green are parallel here, but if you look here, clearly these lines are not parallel. So kind of like a perspective projection in that aspect. So it does not preserve the size, angle, or parallelism. What does it preserve? Collinearity, for example, concurrency. Like what? Like if I had black and red on a line, and let's say another point here, then if these 3 points were on a line, still here, these 3 points will stay on a line. Of course, a different line, different angle, different size, everything, but the collinearity stays. That's the only thing it keeps, but it does the maximum warping you can imagine. Okay, so, and intuitively, what is it? Intuitively, projective transformation is when the observer, or in this case your camera, changes its location or position. So like here, instead of taking a picture from this square with the camera right here, you brought your camera right over here in a completely arbitrary new location, and you took a new image. And then you got completely different set. So this is where you can arbitrarily change the position of the observer or the camera. This is called projective transformation. What is affine? Well, I have a separate video under my MATLAB playlist where I talked about affine transformation. So if you want more details about affine transformation, go to that video. But what is affine and why does it have 6 degrees of freedom? So what does it do? An affine has 6 parameters. These 2 parameters here, or these 2 that we call C1 and C2, have to be 0. It only has 6 parameters, A1, A2, or A1, 1, 1, 2, 2, 1, 2, 2, and Tx and Ty. What's the role of them? These 2 will do translation for you. They translate the image. If this 2 by 2 that you see, if this 2 by 2 is an identity matrix, it doesn't do anything. If it's a diagonal matrix, like for example A11, 0, 0, A22, what does this one do? This is doing scaling. It does a scaling of A11 in the horizontal direction. It does a scaling of A22 in the vertical direction, or A11 in one and A22 in the perpendicular direction. So this is a scaling only. Okay. If it does a form like a rotation matrix, so like this element is like cosine of theta. Let me write it with general cosine and sine, not C and S, because that's what we use in robotics. Might confuse you. So if it's like a rotation matrix, then all it does is a rotation by angle theta. So here, these off diagonals are what? Not 0 anymore, but you see they are related. They are all related to the same angle theta. If in general it is arbitrary form like this, where these a's are not related to an angle and the diagonals are not 0, for example, if it has something like this, A, B, C, and 0, or let's say A, 0, C, and D, or B. These 2 are doing scaling. This one is what it does, what we say shear or skew. It does the shear on the image. You can also add an element here. This is shear in one direction. This is shear in the perpendicular direction. Okay, so it might be like horizontal shear, vertical shear. Okay, so the effect of affine is in general translation, rotation, scaling, and shear. And so far I have shown you how to do translation separately with IM translate, this one with IM resize, and this one with IM rotate. The only thing you have not seen so far is the shear. How do we do shear on the image? So I'm going to show you that in an affine transformation by selecting one of these 2 off diagonal elements to be non-zero. That allows for a shear, and I'm going to show you that, and then I'll show you how to do a projective deformation. Now, what's the difference between affine and projective intuitively? Remember, I told you in projective, you do convert a square into a quadrilateral. You select 4 points, convert them into new 4 points. In affine, you don't really need 4 points. You can only select 3 points. Project them onto the new 3 points. The 4 point is automatically calculated for you. Why? Because this one preserves something the previous one didn't, and that is parallelism. In here, if you look, if this line here and this line are parallel, here they are also parallel. If this line is parallel with this one, again here they are parallel. Right? So because it saves parallelism, if I have these 3 points, what do? From this blue point, I draw a line parallel to the line connecting green and red. And then from the red, I draw a line parallel to the one connecting what? The green and the blue, like this. And what's that going to give me? Of course, the intersection point, the new point. Okay, so because of parallelism, I only need to transform 3 points, not 4. So it's a transformation of a triangle, not a square. Okay, now let me show you both of them in the code. Here we go. So if I run the code one more time and show you the original image, whatever it was, you can see here, and now look at these new versions of the image. So these are the two Phillips which I showed you. Here, this is the shear. If you look at it compared to this, you clearly see in the horizontal direction there is a shear. So the square is converted into a parallelogram. Why? Because if you look here, how did I do it? First of all, what command would you use in MATLAB to do that? The command is called IM_transform. What you pass to the IM_transform is a transformation matrix. How can you make a transformation matrix? The way to go about it is another command is called make_tform, make a transformation matrix. So that command make_tform, you can either pass to it a completely custom transformation matrix 3 by 3, or you can pass specific keywords so it knows what kind of format it should create. If you say, I want an affine one, and then you pass an affine transformation, it makes an affine. If you say, I want a projective, then it makes a projective. So first, using the command make_tform, create your transformation matrix, and then apply it to the image using the command IM_transform, okay? And the variable T forms that you form, they are not a matrix. They are not a simple matrix. They are structures. So if I say here T_form_1, it is a structure. It's not a 3 by 3 matrix. You see, it has endims in 2, endims out 2, and then it has some forward and inverse function, and it has T data. If I show you T_form_1 T data, then under the T, you see that matrix that you gave it. So here, this is the matrix that here I passed to it. So it involves a little bit more information than simply the matrix. It has more than that. It's a structure. And if you look at this matrix, clearly you see these projective elements are 0. There is no translation. If you look at this one and this one, Tx and Ty are 0. The diagonals are 1, so there is no scaling. There is no rotation. The only thing you have is this off diagonal 0.5, which makes a horizontal shear. Now, if I wanted to make it vertical shear, I made this one non-zero. I made this one 0. So here is what I have. Now I'm going to make this one 0 and make this one 0.5. And that one should give me the vertical shear, as you can see here. Look at that, this one. You clearly see compared to last time that the shear was done horizontally, so the parallelogram was basically stretched this way. Now it is stretched vertically, or you can use both of them at the same time. So this is how to do shear with the image, which is changing angles. Basically, you can change the angles, but you cannot change parallelism. Okay, but in projective, you can do literally whatever you want. So how did I define a projective here? Instead of me giving it a matrix like this, I said, well, I give you the coordinates of the blue, red, black, and green points, the square, and I tell you where to put them using this projective. I give you the new coordinates of them. Using this set of points, you calculate for me what kind of projection I need. So here, I say the original points are 0, 0, 1, 0, 0, 1, and 1, 1, right? Clearly, they form a square. And the new coordinates of the equilateral vertices are these: -4 and 2, -8 and 3, -3, -5, 6 and 3. And then based on that, you calculate for me T form 2, and then what? You do the projection for me, which you can see right down here. If you look at this one versus this, clearly you see parallelism is not conserved. If you look at the two legs of the small table, you clearly see that they are parallel, while here you see they are kind of diverging or converging if you zoom a little bit further. Right, let me see if I can show you over here. If you see, the divergence is quite clear, or convergence. So it acts like, as I said, the perspective projection. And so if I want to know what matrix it was, let me show you T form 2, right? And then I can say T form 2 dot data dot T. No, it doesn't have T, does it? Let's see, yes, it does. So this is the matrix. Clearly you see this element is 1 and all other elements are arbitrary, not arbitrary, they are calculated, but they are not necessarily related to each other. They are forcing those 4 points to be projected to these 4 points. And that is the projective transformation that you need. Okay, so similarity, let me just mention it since I added that word for you. In similarity, you only have 4 degrees of freedom. Here, you also have to preserve size. You can rotate, you can translate, and you can, actually, you're not preserving size. You are preserving the angles. I'm sorry. So here, let me do that. So you can do scaling. You can do translation and rotation, but no shear. So it's like 0, 0, 1. These two are like tx and ty. You can do translation. This portion, the off diagonals, can not be non-zero unless it comes from a rotation matrix. So it's like basically a times cosine of theta negative sine theta, correct? And then you have a sine theta, and then you have a b cosine theta. So you have a rotation in general, and then you have a scalings a and b in general, or you can scale it both in the same ratio like this. So if your original shape is like that, your similarity transform will be a rotated version, a scaled version, and actually both of them have to be the same a. They cannot be a and b, otherwise the shape will be different. A square will be a rectangle. So they have to be scaled in the same amounts, both x and y. So your 4 degrees of freedom that we talk about is the scaling, is the angle, and the 2 translations. These are the 4 degrees of freedom. So a square is still going to be a square, but maybe bigger or smaller, rotated and translated. But the shapes are going to be similar. So that's why we call it similarity transform. Okay, so you can create all of them using the command make T-form and then apply them using the command im transform here. Okay, so long video, but I told you a lot of important operations on images that you need to know. I will see you in my next video. Thank you.